776, and we're here to talk to you about our team. So I'm Thomas Lemoyne. Thanks, guys. I'm Thomas Lemoyne. I'm a senior, and I work on the engineering aspect of the robot. And I'm going to talk to you guys a little bit about our engineering process here at 7776. This year it's been a little bit different. We've kind of transitioned to using CAD a lot. So we actually like to design everything in CAD before we actually build it. And that's been really beneficial in terms of kind of figuring out, weeding out exactly what our idea is going to be before we actually build it. So we can makes ordering parts easier and just building it pretty easy. So for our chassis, as you can tell, it's machined out of acrylic. So basically what we did is we had a design we liked that we had seen from previous years that used the 4 plates of acrylic to sandwich wheels, and then our motors are located in the back. Basically what we did was we kind of CAD'd up a general design just with the 6 wheels where they are and the plastic where it is. And we used 2-inch standoffs because that makes it kind of easy. And basically what we did was we put everything together in CAD first and reviewed it with the entire team. So I worked on the chassis and I designed it, and then I presented it to our team to make sure that everyone thought it was satisfactory. And then we ordered all the parts and machined it on our CNC router we have at school, and then we built it. And for our team, we have a very iterative design process. So we first built the robot or the chassis, and then we found flaws, and then we kind of went through a bunch of different iterations. We had some trouble with chain tensioning and just different stuff, and we kind of gradually progressed until we found a chassis design that we liked and we stuck with it. So, thank you. And Melissa is next. She's going to talk about our glyph mechanism.
Hi. I don't know I'm a senior, and this is my 4th year doing robotics. And I'm going to talk to you about our glyph mechanism. So this year we knew that the glyph transportation mechanism was going to be one of the most important aspects of the robot, because it is where most of the points are scored in teleop this year. And so we wanted to focus a lot of our time and effort into building and designing a successful glyph mechanism. So we had 3 different main iterations of the glyph mechanism. We started out with a clamp-like mechanism, which had 2 plates that were attached by a rack and pinion that moved them back and forth, that clamped the glyphs pretty much to transport them into the crypto box. And that was a very basic design that we wanted to just use for the first couple of needs. So we knew that it wasn't going to be a permanent thing on the robot. We just wanted to be able to score glyph points in the beginning tournaments. So we knew that we wanted to move on to our second iteration, which is very similar to what we have right now, but it was never actually used on the field. It was more of a proof of concept design, and it helped us figure out what we wanted to do with our final glyph mechanism design. So what it had was, it was similar, except instead of having 4 continuous rotation servos, it had 1 motor with chain that moved the 4 wheels that were not squishy wheels. And we found that that was a problem because not all the blocks are the same size. And then also the board flexed, and that was a major problem with chain, and also it's not legal. So we kind of went back to the drawing board, and we came back with 4 continuous rotation servos with no chain, squishy wheels. That'll pass inspection. Yeah, so basically it's going to it intakes the glyphs into this contraption, and then it puts it in the back. And once we have 2 glyphs, this lift on the back raises up and scores it in. And this is Noah, and he's going to talk about autonomous.
Hello, I'm a senior. I've been on this team for 4 years. So last year we went the farthest our team has ever been to super regionals, and we built the most complex autonomous our team has ever built. And we, going that distance and having our autonomous trialed by many, many different tournaments and many, many different situations, we learned a couple of lessons. First and foremost, we always want to have an autonomous that scores a set amount of points no matter if everything is broken. One of the things we found out in the original qualifying tournaments last year is that even though the robot barely moved, we were still able to shoot 2 balls into the center vortex, which scored us 30 points, and that set us way far ahead of the competition, which was a huge benefit, even in the bigger tournaments, where we could score massive amounts of points, but those little points mattered. Always have a minimum viable product. The second lesson we learned was that we had this great camera detection system for following the line in front of the beacon, and that was the only method of detecting that line, since we figured that was all we would need, because we figured we would just test it and test it and test it until it worked always. As you can imagine, that didn't work. As it turned out, there were spotlights at super regionals, and that screwed up our autonomous. Lesson learned, always have multiple methods of detection when you're working with an autonomous robot, because sometimes you just can't predict what you don't know. So this year, we've developed multiple methods of determining or detecting all of the point obstacles on the field, with the exception of the VU mark, which I have not figured out how to do yet. So first of all, the first obstacle we go for, our minimum viable product, is the 2 joules, which is right next to the robot when we balance on the platform. That's in order to detect those, first of all, I use the phone's camera, which using an image over here can actually determine the location of the 2 joules over here, and using the camera it determines position and then the color, and then given those 2 variables it can use this stick over here to whack the correct joule, which Benjamin will talk a little bit more about later. The other method of detection, which we use as a backup, is mounted on this stick. You can see a sensor here, and there's also supposed to be a sensor on the back. These also sense ambient light and therefore color, and so in the event of a failure of Vuforia or harsh lighting and the camera doesn't work, we can still detect the color of the balls, since these will be in extremely close proximity to the balls themselves. Our next goal was to score a block in the correct CryptoBox pillar. Our first solution to that was the camera, since it was readily available and right on the side of the robot. We just drive past the CryptoBox pillars, and then using the camera, since the CryptoBox pillars are very long and a dominant color, we use what's called a histogram, or finding large blocks of blue vertical columns, and then using a bunch of thresholds, we can say, okay, there's a pillar here, there's a pillar here, there's a pillar here. You're going to drive to X position, since you're looking for X column, and then turn the robot and dump it into it. The alternative is these sensors over here also detect not only color, but distance as well, using an infrared diode and an infrared sensor. So I can stick my hand in front of here, and it'll tell me the number of millimeters. So by sticking this out into the pillars as we drive by them, we can say, okay, I've gotten to 1 pillar, and then pull it back, drive past, drive forward, and push it forward again. Okay, I'm going to the 2nd pillar, and we can count each pillar we go by, determining the robot's location relative to the pillar, and scoring the block on the correct pillar. And next, I'm going to pass you off to Benjamin, who can give you more details on the Wacky Stick itself.